All right, guys. Hope you're all doing well. Coming at you with the very first lecture video for chapter number 14 here, which is all about acids and bases. Now, I'm sure you've heard of acids and bases in the past, most likely. Possibly even talked about something like called the pH scale and talked about acidic pH versus basic pH, stuff like that, right? We'll reserve some of that pH conversation for later on this chapter. It's still very much applicable to this chapter, absolutely. But for the very beginning of chapter 14 here, a lot of what I want to kind of focus in on are, of course, kind of just talking about some of the definitions for what acids and bases are, right? Always important to kind of talk about some vocabulary to start a chapter so that you can then utilize that vocabulary as you progress through the rest of the chapter, right? So it's no different than a lot of the chapters we've done in the past, and going to be something we do very much today in this lecture video. So one of the very first definitions, there's really going to be three main definitions of what an acid is. Now, of the three definitions, we're really only going to focus on two of those definitions of what an acid is. The first one here is known as the Arrhenius, A-R-R-H-E-N-I-U-S, Arrhenius definition of an acid. Now, it's important to recognize the fact that I'm calling this the Arrhenius definition of an acid, right? Because there's going to be a different way to call something else an acid later on as we progress through chapter 14 here, okay? But this particular definition is called the Arrhenius definition of an acid. And the Arrhenius definition for an acid is a substance that produces H plus ions in solution. H plus ions in solution. And again, this is specifically called an Arrhenius acid. So for example, something like HCl. Now, this is a substance, HCl, also known as hydrochloric acid, that we have utilized in the past, several times actually in the lab environment, HCl being hydrochloric acid again. Now, this particular substance, HCl, is called or can be referred to as an Arrhenius acid because when you take HCl and you mix it with water, okay, and you create a solution out of it, this particular substance, HCl, produces these H plus ions in the solution of water, right? So an aqueous solution of HCl is going to produce these H plus ions that you're looking for, right? And any substance that does that, right, when it mixes with water to produce a solution, if in that solution there are H plus ions hanging around, it's because that's referred to as an Arrhenius acid, all right? Again, it's the H plus, right? It's the presence of this H plus ion in the solution that allows you to determine that there is an acid present, specifically an Arrhenius acid, okay? Now, of course, there are still plenty of additional pieces in our reference table that we're going to continue to talk about, and the very first one we're going to talk about here in chapter 14 is going to be table K here, right? So if you've got your reference table somewhere nearby, you can certainly take a look at table K to see all of the different types of common acids that you might see throughout this chapter or really the rest of the school year, okay? Table K is your list of common acids. Now, the next thing here, which are the complete opposite of acids here, guys, they're going to be known as your bases. And specifically here, we're going to be talking about what's known as an Arrhenius base. Now, bases, Arrhenius bases particularly, are substances that produce what's known as an OH minus ion, okay? It's a little bit different than the H plus, right? H plus ions are different than acids. Arrhenius acids are producing H plus, whereas Arrhenius bases are producing OH minus ions in solution, right? And these, again, are specifically referred to as Arrhenius bases. Now, this right here is a great example of an Arrhenius base. And this one in particular is another substance that you guys have utilized in the lab environment called NaOH, or sodium, Na, and OH being hydroxide, right? Hydroxide being one of those polyatomic ions that we've seen so many times in the past on table E in your reference table, right? So NaOH, sodium hydroxide, right? Now, NaOH, or sodium hydroxide, is referred to as an Arrhenius base because when you mix this NaOH in water, right, to produce a solution, an aqueous solution, hanging out in that aqueous solution, guys, are those OH minus or those hydroxide ions, right? So it's the presence of these hydroxide ions that allow you to essentially determine this is an Arrhenius base. Now, you might be thinking to yourself, hey, well, I can actually just look at any kind of formula, any kind of chemical formula I want, and provided that I see this OH in the formula like you do see here in NaOH, right? If I see this OH present here, yeah, awesome, great. it's got to be a base, right? An Arrhenius base particularly. Well, that's actually not necessarily the case, okay? Any substance with a carbon or a carbon-containing group that has this OH is not necessarily a base here, right? So, for example, there are two examples right here of CH3OH and CH3COOH that are actually not bases, right? And the reason why these are not bases is because these are carbon-containing groups, right? Both of these formulas have this carbon atom at the very, very, very front of the formula, right? Present inside of the molecule here. And because this is a carbon or carbon-containing group here, right, like it says in this definition right here, right, even though there is this OH in the formula here, right, just the mere presence of OH does not necessarily mean that this is considered to be a base, right? When we look at OH over here and NaOH, right, it might be easy to assume that this substance right here is going to be a base, right? But the reason why this is a base, guys, is because it's going to make a solution of OH minus ions, these hydroxide ions, but there's also no carbon present, right? This is just sodium. Whereas in this example here, right, of CH3 and CH3 over here, well, there's carbon in both of these. And if there's a carbon-containing group with these OHs, they're not going to actually be bases. These types of substances are actually called alcohols. These are organic alcohols specifically, right? So again, absolutely, right? If you see that capital C, right, specifically carbon, that does actually, that's exactly going to mean the opposite of a base, right? It's something totally different called a organic alcohol, right? Now, similarly to table K, which has all of your different types of common acids, we now have this table L here, guys, that's going to have a list of different types of common bases that you could also take a look at in your reference table. It's actually going to be just below table K in your reference table, so it has a bunch of bases on there. Now, also, it's important to talk about different types of properties and whatnot, right? So we're going to talk about some properties of acids in this slide here. Now, dilute solutions of acids are going to have a sour taste. They're going to be aqueous solutions that conduct electricity, and these are going to be referred to as electrolytes. They react with metals to produce hydrogen gas. And they're also going to turn indicators certain colors. Now, I'm sure you guys in the past, maybe in like a middle school science class, you guys have used something called litmus paper. And litmus paper is a pretty common one to showcase a couple of different things when it comes to acids and bases, right? But litmus paper, that's going to turn a red color in the presence of an acid. So litmus paper will turn red. Phenolphthalein is going to be clear. And we'll talk more about this phenolphthalein stuff. It's a pretty particularly long word here, right? Phenolphthalein. But this particular substance here is another type of indicator that's going to actually be the basis for the lab that we're going to be doing sometime very, very soon. So look out for this phenolphthalein again sometime in the near future here, especially in the lab environment. Now, as we talk about indicators, it's also going to bring forward into the front this idea of talking about table M, which is in your reference table as well. It's got a list of other indicators that we're going to talk about throughout this chapter as well. Okay. Now, coming at you are a list of all the different types of properties of bases you are going to start to having to know here, right? Sometimes bases are referred to as alkaline. They have a slippery or a soapy feeling, right? So if you ever washed your hands, which I hope you all have, right? You know, it seems like soap, for example, is a very slippery type of substance, right? And obviously soapy feeling because it is soap. But, you know, soaps are generally kind of slippery, right? And because a lot of soaps are going to be more so a base, actually, right? And so a physical property of a base here is actually that the fact that a lot of bases are quite slippery, okay? Now, in terms of taste, bases are going to have a more bitter taste as opposed to sour, which is the opposite of an acid. You know, an aqueous solution of bases are also going to be conducting electricity as well, also considered to be good electrolytes. And then when it comes to indicators, they're going to turn also some very, very specific colors. Litmus paper is going to turn blue. And this other phenolphthalein stuff that I was referring to, right, that you'll be encountering in your lab very soon, is actually going to turn pink, right? So the different colors you've seen so far with this phenolphthalein stuff has been clear as well as now pink. Okay, so it's a pretty interesting indicator of this phenolphthalein, and we're going to get really well acquainted with it very, very soon in the lab environment. And again, you can look at table M for some more indicators that are going to be very specific to bases. Okay, we got one more slide here, which has got a little bit more information on acids and bases as a whole. You know, oftentimes when it comes to sort of the damage that can be incurred on organic substances like skin and whatnot, we like to use these words as caustic and corrosive, right? Acids and bases are sometimes going to be caustic and corrosive, right? And it just kind of shows you the sort of the threat level that these acids and bases can have. Now, this threat level does in fact depend on a couple of different things, right? It's not just like you've got an acid, for example, and this acid is going to just rip the skin off you, right? I told you guys this in the past, especially in the lab environment, right? When we first used our HCl, our hydrochloric acid before, right? A couple of you guys have got it on your skin, right? And your skin is absolutely not melted off, okay? That's because there's a degree of threat that is handled when it comes to acids, right? Sometimes they're very, very strong, and sometimes they're very, very concentrated, and that's going to obviously increase their threat level. But if you don't have a very, very strong or a very, very high concentrated substance, that's going to obviously, significantly plummet the threat level that acid or that base is going to have, okay? But that is going to be it for our notes here, guys, today. We're going to pick up next class with this sample question as well as a couple of other ones. So I will see you guys then. Have a good rest of your day.